What's up, everybody? Today we're going to be looking at what I consider the top 5 AP Physics test questions in the subject of energy. So I can't guarantee that all of these will be on there, but for sure 2 or 3. And if you know all these concepts, you should be in really good shape. All right, let's take a look. So the number 1 question type should be of no surprise, and that is conservation of energy. And you'll probably get several of these questions, to be honest. The key is you look at like what energy there is at a certain location. So whether that's kinetic, whether that's gravitational potential, spring potential, or both. And then you just say, well, whatever the energy is there, it's going to be the same somewhere else. So if my energy is 10 joules at one place, it should be 10 joules at another. For example, let's say you have a mass moving, it goes up a ramp. Let's say a mass is moving, a certain speed down here. It has kinetic energy down here. Let's say, you calculate it and you get like 10 joules, for instance. And it goes up a ramp, and up here, it slows down. Let's say you calculate the kinetic energy to be 3 joules. Well, you know that it must have gained a potential energy of 7 joules. Or let's say you have a mass up here, has potential energy, gravitational, and let's say it falls down onto, say, a spring, right? And it's going to compress it a certain amount, and now it has spring potential. Or here's a favorite. You have a mass moving with, say, kinetic energy, and it bumps into a spring. And it compresses the spring a certain distance, and now it turns into spring potential. Or what about a rolling problem? What if you have a ball that's rolling down a ramp? Let's say it starts at rest, so it has gravitational potential, and then it rolls down, and now at the bottom it has both translational kinetic energy plus rotational kinetic energy. So anyways, that's about it. That's all you need to do. Just make sure you notice all the types of energies at certain locations. Maybe we can just summarize some. We have gravitational potential energy, that's mgh. We have spring potential, that's 1/2 kx squared. We have translational kinetic energy, that's 1/2 mv squared. We have rotational kinetic energy, that's 1/2 I omega squared. One last thing you might see also is work. In work, we'll usually either add energy or remove energy. So for example, let's say this ball is rolling. Let's say it has like 5 joules plus 5 joules of each. And let's say you're right here and you want to stop the ball. Well, you would need to do work of 10 joules to stop the ball. So it's not exactly energy, really it's transferring energy into different types, but sometimes you will have to think about work as well. So that's a good transition to the second most common question you'll see. So the second most common question, this is energy lost, calculating energy loss, which is oftentimes asked as kind of a negative work type question. And really you do the same thing you just did. You find the energy at 2 different locations. And typically they'll be different. And then in that situation, you just find the difference. And that's how much energy is lost or how much negative work is done. So for example, let's look at the problem we just did. Let's say instead of having 3 joules of kinetic at the top, you have 7 joules of potential, but you only have, let's say, 1 joule. Well, in that situation, notice that we're ending up with 8 total joules of mechanical energy. And so that means that you had energy lost of 2 joules, right? And oftentimes we'll say, how much work was done by friction? So maybe there's like some friction on this ramp, for example. Well, you would just simply say 2 joules of work was done by friction. Now, is this positive work or negative work? Well, since energy is being removed from the system here, we would say it's negative work. Or perhaps you have the bouncy ball problem, one of the test writer's favorite questions. So you have a ball, for example, It bounces, it goes to say a lower height, and there's going to be some energy lost in the collision. Well, just find out how much energy is up here. Let's just say it's like 10 joules up here, and let's say it's like 7 joules up here. Then you'd say, oh, the energy lost in the collision was the difference, 3 joules. Okay? Just to continue on this question, typically that happens in the bounce. So for example, there would be 10 joules right here before it hits the ground, and then right here there would be 7 joules right after the ground. So I've seen them ask questions, for example, how much energy is there right here? And again, you would just calculate that it's 7 joules. Third most common question you'll see is actually a graph, interpreting a graph, a force distance graph, or sometimes a force position graph. And the key thing you need to know for this is that the area under this curve is going to be the work, and then work is going to also be the change in kinetic. So for example, maybe you're given a graph like this, and the question is how much work is there, and you just find the area underneath it. So for example, you can see there's a nice triangle here. This would be 1/2 times 30 times 8, which would give us 120 in this region, joules. And then you find the area of this rectangle right here, which would be 30, and then this distance is 4. 30 times 4 is also 120. So what's the total work? You would say 240 joules. Now that would be for the total 12-meter distance, right? But maybe they ask about 8 meters, in which case the answer would just be 120. Sometimes actually they don't even ask for work. They ask for, oh, what's the kinetic energy or the change in kinetic? Well, remember that's the same as the work, 240 joules. Or maybe they give you the mass. They say, okay, the mass is 2 kilograms. What's the velocity final? And then you just know, oh, well, kinetic is 1/2 mv squared. And since I know that's 240 and the mass is 2, then v would just be the square root of 240. So just remember the area of a force versus distance graph will tell you work, and you can also get the change in kinetic energy from that. Question type number 4 is, again, kind of a work question, but this time just understanding that work is force parallel to distance. So for example, if you are pushing, you apply a force on a mass and it goes like a distance this way, just remember that you need that component of force that is parallel to the distance that it moves. So this would be, for in this example, if this is an angle theta, you just write F cosine of theta times the distance. That's going to be my work. Or another example might be, let's say you're carrying like a box or something this way with the distance. Well, if your force is straight up and your distance is horizontal, then the answer is actually going to be 0. It's a trick question they sometimes give. Or maybe another trick question similarly would be, maybe something's moving in a circle. Remember, the force is always perpendicular when things are in a circle, and the work again would just be 0. Or another example might be an inclined plane. Maybe you're pushing a mass with an applied force up the ramp, and let's say gravity is going to be pulling back down. Now it's not mg, in this case this is our horizontal component, which would be mg sine theta. So you'd have to push it up the ramp with the force of mg sine theta. Let's say it's a constant velocity. So your applied force is mg sine theta times the distance of the ramp here going up. Interesting enough, if there is kind of no friction in this problem, you could also treat this, like imagine you have an object here and you're going to push it to the same height. Well, in this case, you'd have to lift with an mg value going up, right? Mg is down, your force would have to be mg. So your force to get it up the ramp would be mg. Your work would be mg parallel. This time you would care about the height because that's parallel to your push when you're just lifting it up the ramp. I guess that'd be more like a pull, right? In that case, you'd be mgh. Now notice the relationship between these. Sine of theta is equal to h over d. Well, if you say h is then d sine theta, boom, you put that h in there and you get mg d sine theta. The exact answer that we had right here, right? So anyway, just remember that work is not force times distance, but it's force parallel to distance. So the last question type I have for you today is actually a more recent favorite. You've only seen these come up in the last 2 or 3 years, but this is to create these energy bar charts. And you really kind of approach the problem the same way, where you look for the energy, the amount of energy at each location, and then you just make a little bar chart based on how much energy you have. Just remember that the sum of energies always has to equal the total, and then there will sometimes be energy lost in the problem. So I just want to give a shout out to Physics Classroom. They actually have a very good thing called a concept builder, and all of them are excellent, but their one with energy bar charts is exceptional. So take a look over there and you can do some practice with these. I definitely recommend that. But let's say, for example, let's say here we're at point A, and you can see we have 0 kinetic there. We have all potential energy, gravitational, and then this TME is the total mechanical energy. So notice at point B, we have lost some potential energy and we have gained some kinetic. But notice the total mechanical stays constant. So C, you're going to notice that we have more kinetic and less potential because we're a little bit lower, right? And that's all you do. And notice that total mechanical stays the same the whole time. Okay, at D we have all kinetic and 0 potential. E we have a little bit of kinetic, a little bit of potential and mostly kinetic. And the total, again, stays the same. You do want to make sure that the totals add up. So for example, if you have 5 units, then you always want to have 1, 2, 3, 4, 5 units all the way through. Let me change the problem a little bit. Let's say, what if there's friction here? So for example, let's say there's friction. Let's look at what B might look like if there's friction. Well, the total, so we'll call this like energy lost, or sometimes they'll say work of friction. So we'll call this work of friction. Here's all the things they might call it. Work of friction, they might call it heat or thermal energy. Okay, they might simply say energy loss or lost. So anyways, let's say we lose a little bit. So let's say we lose 1 unit. So when you draw this out, you would draw the total would drop by 1 unit. And then we'd need to lose, say, 1 unit of kinetic. So maybe our kinetic goes up to here and our potential goes up to here. You just want to make sure the total still adds up to 5. So let's say we have like 1, 2, 3 units of mechanical energy, and so 1, 2, 3, oops, that's 4 units, right? 4 units of mechanical energy, and then here's our 1 unit that got lost. Or let's say we progress to point C. Now maybe we lose 2 units of thermal energy. And that means now we have 3 units of total mechanical. And so maybe the kinetic is right here, 2 units, and the potential is maybe 1 unit. So that's all you do. Let's go to D. Let's say we lose another unit. So now we're down to 2 units of mechanical, and we're up to 3 units of thermal, right? And so now maybe our kinetic, or we have 0 potential, right? So that means our kinetic here would be this full 2 units. All the mechanical energy would be 2. Just finish it up. Let's say we lose another unit of mechanical energy. And how could we draw this? Well, it's mostly kinetic. Your potential is teeny tiny. Maybe your kinetic is a little bit more, right? And then your thermal is 4. So anyway, I definitely recommend taking a look at the concept builders on Physics Classroom and playing around with those. Those help you a lot. So anyway, those are the 5 most common energy questions. Please let me know if these show up. If any of these show up, if all of them show up, that'd be amazing. I know some for sure will show, but let me know how much show up on the test. All right, good luck, everybody.